So in this lecture, I would like to discuss about the molecular orbital energy level diagrams of oxygen, fluorine and neon molecule. So I am going to draw here that diagrams. In the previous lecture, we has been discussed about how there is a formation of molecular orbitals takes place. Bonding molecular orbitals, anti-bonding molecular orbitals, then sigma molecular orbitals, pi molecular orbitals, and we has also draw the some MO diagrams of the molecule like H2 molecule, lithium molecule, beryllium molecule, then helium molecule. So today I would like to draw the remaining MO diagrams. So it is very easy to draw the MO diagrams. So you can see now how the MO diagrams can be drawn here. So let us draw the MO diagram of the oxygen molecule first. Molecular orbital diagram of oxygen molecule, O2 molecule, O2 molecule. First of all, we have to write the electronic configuration of the oxygen atom. So it is having the electronic configuration 1s2, 2s2, 2p4. 2s2, 2p4 is the valence shell where 6 electrons are there. So in oxygen molecule, total number of electrons are equal to 16. 8 for one oxygen, 8 for other oxygen. So in the molecule, there are total 16 electrons. Now, to draw the MO diagram, first of all, we have to represent the atomic orbitals and molecular orbitals are according to the increasing energy level. So draw such arrow line where atomic orbitals and molecular orbitals are according to the increasing energy level. So first of all, on the left side represent the atomic orbitals of oxygen atom. Similarly, onto the right side, atomic orbitals of oxygen atom. And middle part, it is the molecular orbitals of O2 molecule. So in the electronic configuration, there are 1s, 2s and 2p. So represent here these orbitals as like of this 1s orbital, then 2s orbital of oxygen and 2p orbital. 2p orbital, okay. So we represent here the energy level of these orbitals 1s, 2s and 2p. So let us write here 1s, 2s and 2p. There are 3p orbitals 2px, 2py and 2pz. 1s, 2s only one, 1s is only one. Similarly on this side, the atomic orbitals of the oxygen atoms, they are having the same energy here. This is 1s of this oxygen, then 2s of this oxygen atom and 2p of the oxygen atom, 2px, 2py, 2pz. Now let us put the electrons in the atomic orbitals. So 1s2, then 2s2 and 2p4. Similarly, for another oxygen atom, 1s2, 2s2 and 2p4. 2p4. Okay. Now let us represent the overlapping between the atomic orbitals of the two oxygen atoms. We know that when the two oxygen atoms are approaches towards each other, their atomic orbitals get combined and molecular orbitals are formed, and on the same time the oxygen molecule is also formed. So first orbital, it is of course 1s, but this 1s orbital does not involve into the bonding. It remains as non-bonding. So no bonding is there because this 1s orbital belongs to inner shell, inner electrons. They are not belongs to valence shell. So no bonding is there. Now let us take 2s atomic orbital of the oxygen atom. It can be overlapped with 2s atomic orbital of the other oxygen atom. So we can show this overlapping. Okay. So 2s can overlap with 2s. There is a formation of bonding molecular orbital and antibonding molecular orbital. Formation of bonding and antibonding. So which bonding molecular orbital can be formed? 2s overlap with 2s gives two molecular orbital. One it is sigma 2s and other it is sigma star 2s. So lower energy orbital it is bonding sigma 2s and higher energy orbital it is antibonding sigma star 2s. Now next orbital it is 2p orbital. So there are 3p orbitals, that is 2px, then 2py and 2pz. This is for one oxygen atom. Similarly, for another oxygen atom, the same orbitals are there, 2px, 2py and 2pz. All these orbitals are having the identical energy. Now out of these 3p orbitals, we know that 2pz orbital when overlap with 2pz orbital, it gives two molecular orbitals, that is sigma 2pz bonding molecular orbital and sigma star 2pz antibonding molecular orbital, and remaining two orbitals, that is 2px overlaps with 2px, it will give pi 2px and pi star 2px pi bonding molecular orbital, because 2px and 2py atomic orbitals are suitable for the formation of the pi bond. So first of all, the 2pz orbital of the oxygen atom get overlap with 2pz orbital of the other oxygen atom. Okay. Formation of bonding and antibonding molecular orbitals, that is sigma 2pz. This is sigma 2pz and this is sigma star 2pz. Okay, sigma star 2pz. So put the circles here in the bonding and antibonding molecular orbitals. This is one bonding, one antibonding, one bonding, one antibonding. Now remaining 2px and 2py also overlaps with 2px and 2py orbital of the other oxygen atom, and there is a formation of the pi bonding molecular orbital. So we can show in the diagram. 2px get overlap with 2px and 2py get overlap with 2py. Formation of pi 2px and pi star 2px antibonding molecular orbital. Pi 2px and pi star 2px antibonding molecular orbital. So you can see here the MO diagram of the oxygen molecule. See here, it has been already given. So this slide represents the MO diagram of the oxygen molecule. So see here, the pi 2px and pi 2py pi bonding molecular orbitals are formed here. Now these pi bonding molecular orbitals are having the same energy. They are having the same energy because same type of the pi bonding molecular orbitals are formed. So we cannot differentiate between these two. Similarly, these pi star to px and pi star to py, antibonding molecular orbitals. And last one, it is sigma star to pz. Okay. Now in this case, the energy difference between this pi bonding and pi antibonding, it will be less as compared to sigma bonding and sigma star antibonding. This is because during the formation of the sigma molecular orbital, there is a appreciable overlapping between the atomic orbitals. So this energy gap is larger between bonding and antibonding. But in case of the formation of the pi bonding molecular orbitals, the energy gap will be less because there is a lateral overlapping or sidewise overlapping between the atomic orbitals. Okay. So that's why this energy gap between bonding, pi bonding and pi star antibonding is less here. So antibonding are below to this sigma star antibonding here. Now let us feel the number of the electrons, distribute the electrons into the various molecular orbitals from lower energy orbital to the higher energy orbital. Okay. Now as this 1s electron not participate in the bonding, so don't consider them. Next, these 2 and these 4, 6 plus 6. So there are total 12 electrons. Now we have to distribute, we have to fill the 12 electrons from lower energy level to the higher energy level. According to the Abou's principle, okay, the electrons can be entered from lower energy orbital to the higher energy orbital. It means the in the lower energy orbital, the electrons can first enter, then higher energy orbital. So first of all, sigma 2s, it is lower energy orbital here, 2 electrons can be placed. Sigma star 2s, next 2 electron. Sigma 2pz, next 2 electron. These are the 2 pi molecular orbitals which are having the same energy level. So 4 electrons are there because these are the 2 pi molecular orbitals. So we fill here 10 electrons. Now 2 are remaining. So this pi star to px carry 1 electron and this pi star to py carry 1 electron. We cannot fill the electron as like of this. This is wrong. Okay. Each orbital should be occupied by single unpaired electron. Then pairing will be started. This is the Hund's rule of maximum multiplicity that is known to us. So that's why the first unpaired electron is here, second unpaired electron is here. So this is the MO diagram of the oxygen molecule. MO diagram of the oxygen molecule. So after the distribution of the electrons, from this MO diagram, we can determine the bond order. So first, we can determine the bond order here. So bond order, it is equal to number of bonding electrons minus number of antibonding electrons divided by 2. So it is equal to number of bonding electrons are 8 here, 2 plus this 6. So it is equal to 8. Number of antibonding electrons are 4, this 2 plus this 2. So it is 4. So bond order is 2 here. So between the two oxygen atoms, there is a double bond. Between the two oxygen atoms, there is a double bond where one bond is a sigma bond and other is a pi bond. So this is about the bond order. Next, we can explain the electronic configuration of the molecule on the basis of this diagram. So it is also very simple. So let us write here O2 molecule, its electronic configuration. So whatever the number of the total electrons in the molecule, we have to represent. Even though these 1s electrons are not participate into the bonding, but we have to represent into the electronic configuration. Just like in an atom, we represent the electrons in the inner cell. Okay. So in this case, we have to represent the electrons. So let us represent in this 1s orbital there are 2 electrons, so we cannot write here 1s. We have to write here K for 1s. K cell have 2 electrons. Similarly, K for this 1s. Okay. Then next now, bonding molecular orbital sigma 2s. How many electrons are there? 2. Sigma 2s 2. Next, sigma star 2s, antibonding molecular orbital, sigma star 2s 2. Next, sigma 2pz. So according to the increasing energy level, we have to write the molecular orbitals. Next it is pi 2px equal to pi 2py. Why we write here equal to symbol? Because they are having the same energy, identical energy. How many electrons are there? 2 electrons. Then next, pi star 2px equal to pi star 2py, antibonding molecular orbital. So it is having 1 electron. So this is the electronic configuration of the oxygen molecule. Okay, the electronic configuration of the oxygen molecule can be written in this way. Now third, the magnetic behavior of the oxygen molecule. Magnetic behavior, magnetic property. So magnetic behavior can be explained on the basis of this MO diagram. You can see in the MO diagram, there are 2 unpaired electrons in the antibonding molecular orbital. And as there are unpaired electrons, then the oxygen molecule, it is paramagnetic. So the magnetic behavior of the molecule, it is paramagnetic. It is paramagnetic. Okay. So try to understand about this. The oxygen molecule, it is paramagnetic molecule because there are 2 unpaired electrons in the pi star antibonding molecular orbitals. There are 2 unpaired electrons in the pi star antibonding molecular orbitals. So on the basis of this MO diagram, we have to explain bond order, electronic configuration and magnetic behavior. And we also understand how many number of the bonds between the 2 oxygen atoms. There are double bonds. Okay, double bond between the 2 oxygen atom. Okay, so this is the explanation for the oxygen molecule. Now let us draw here the next molecule, MO diagram of the next molecule. So I would like to represent that next molecule here. You have to see MO diagram of fluorine molecule. MO diagram, molecular orbital energy level diagram of F2 molecule. By the same way, now we have to draw the MO diagram of the F2 molecule. Okay. So let us write the electronic configuration of the fluorine, atomic number 9. So it is having the electronic configuration 1s2, 2s2, 2p5. So there are 9 electrons. In the valence shell, there are 7 electrons. Okay. So try to draw here the MO diagram of the fluorine molecule. It is as like of the oxygen molecule. In fluorine molecule, there are total how many number of the electrons? There are total 18 electrons in the fluorine molecule, 9 from one fluorine atom. Okay. So let us write here atomic orbitals of fluorine. Similarly here atomic orbitals of fluorine. And middle part it is molecular orbitals of F2 molecule, fluorine molecule. So first one it is 1s orbital of fluorine. 1s orbital of fluorine. Similarly on this side, which is having the same energy. So these horizontal lines are same. So this is 1s, this is 1s. Then 2s orbital of one fluorine atom. So take 2s here. So 2s orbital. Then 2s orbital of fluorine atom. So take here 2s and finally it is 2p. 2p atomic orbital, there are 3p orbitals. Okay. 2px, 2py, 2pz. In the same way, we are going to draw here the MO diagram of the fluorine molecule as like of oxygen. Okay. Similarly here, we can put the circles to place the electrons. Okay. Now place the electrons now. 1s2, 2s2, 2p5. So 1, 2, 3, 4, and 5. Similarly here, 1s2, 2s2, 2p5. Okay. So total number of the electrons in the fluorine molecule are equal to 19. But now this 1s orbital, it is not belongs to the valence shell, so there is a no overlapping, means no bonding. No bonding is there, so they are remains as non-bonding orbital. Okay, they are remains as non-bonding orbitals. Now the 2s orbital can be overlapped with 2s orbital, and there is a formation of bonding and anti-bonding molecular orbital. So 2s 2s overlap gives sigma 2s and sigma star 2s. So give the designation to this sigma 2s and sigma star 2s. Okay, put the circle here. Next, 2p overlap with 2p. Now there are 3p orbitals as we know, 2px, 2py, 2pz. So first of all, we have to take here 2pz. 2pz, okay. So you can see 2pz get overlap with 2pz. Formation of sigma 2pz, bonding molecular orbital, and sigma star 2pz, antibonding molecular orbital, sigma star 2pz. Now the energy gap between this it is larger here, because as we know that sigma bonding molecular orbitals are stronger. Greater overlapping is there between the 2pz 2pz. Appreciable overlapping is there between the 2pz 2pz. So this energy gap between the bonding and anti-bonding molecular orbital will be larger. Next, now 2px and 2py. So 2px and 2py are goes into the pi bonding. They are suitable for the pi bonding. So there are two pi molecular orbitals are formed here. That is pi to px. Pi to px equal to pi to py. Okay. Pi to px equal to pi to py. Now put the circle here. This is sigma to pz. Okay. Then the antibonding molecular orbital pi star to px equal to pi star to py. Okay. So pi star to px, antibonding molecular orbital. Okay. It is equal to pi star 2px equal to 2py. So this is the MO diagram. Let us distribute the electrons. Now this 1s not involved into the bonding, so don't consider them. This 2s 2 plus 2 4, or there are total number of the electrons, this 5 plus 2 7, 7 plus 7 14. So first two electrons goes into the sigma 2s bonding molecular orbital. Next two goes into the sigma star 2s antibonding molecular orbital. According to the increasing energy level, we have to distribute the electrons. Okay, just like we fill the electrons in the atomic orbital. You can see here, we fill the electron first into the 1s, 1s2, then 2s, then 2p, then 3s. Same thing is here. Sigma 2s first, sigma star 2s later, then sigma 2pz. Okay, then pi 2px equal to pi 2py, pi bonding molecular orbital. Now how many remaining electrons now here? The 7 plus 7 14. So I think we fill 10 electrons here. 4 are remaining. So 4 electrons can be placed here in the antibonding molecular orbitals pi star 2px equal to pi star 2py. So this is the distribution of the electron. Sigma star 2pz is empty. So we can now write the bond order here. Calculate the bond order here. So bond order, it is equal to number of bonding electrons minus number of anti-bonding electrons divided by 2. So see here, count the bonding electrons. 2 plus this 2 4, 4 plus 4 8. So 8 here. Count the anti-bonding electrons. This 2, then this 4, 6 anti-bonding electrons divided by 2. So it is equal to 1. That is, there is a single covalent bond between the two fluorine atoms. And that bond is a sigma bond. That bond, it is a sigma bond, single covalent bond between the two fluorine atoms. Okay. So thus bond order is equal to 1. Now we can write the electronic configuration of the molecule. So electronic configuration of the F2 molecule, it is equal to. So for this 1s we have to write K. Similarly for this 1s we have to write K. K means 2 electrons. It is the first cell near to the nucleus. Okay. So K for 2 electrons, K for 2 electrons. Next it is sigma 2s, sigma star 2s, then sigma 2pz, then pi 2px equal to pi 2py. Both are having the same energy because the orbitals are same, and in the same way these molecular orbitals are formed. Then pi star 2px equal to pi star 2py. So don't write here the next empty orbital because there is no electrons. Put the electrons now here. Sigma 2s 2 electrons, sigma star 2s 2 electrons, sigma 2pz 2 electrons. We can put, there are 2 electrons are there, sigma 2pz 2 electrons, then pi 2px 2 electrons, pi 2py 2 electrons, pi star 2px 2 electrons, and pi star 2py 2 electrons. So this is the electronic configuration of the fluorine molecule. Okay. So try to understand. Now later we can write the magnetic behavior of the fluorine molecule, magnetic property. Magnetic behavior of the fluorine molecule. So MO diagram shows that there are no unpaired electrons. All the electrons are paired. As all the electrons are paired, it is having dimagnetic property. So fluorine molecule, it is dimagnetic in nature. It is having dimagnetic behavior. So this is the MO diagram of the fluorine molecule. Okay. So the MO diagram of the oxygen molecule, fluorine molecule, only 2 electrons are additional there. In the oxygen molecule, we know that there are less, 2 electrons are less. See now, this is for the oxygen molecule. Okay. In oxygen molecule, there are, you can see here, this is the MO diagram of the oxygen molecule, only this difference. So oxygen molecule is paramagnetic, but now in fluorine molecule, all the electrons are paired, so it is dimagnetic. So this is the MO diagram of the fluorine molecule, and there is a single covalent bond. Now let us going to draw here the MO diagram for next molecule, that is the neon molecule. Okay, neon molecule. So we have to draw here the MO diagram of the neon molecule, Ne2. Okay, so let us write the electronic configuration of the neon. Electronic configuration of the neon. Okay, so neon atom, it is atomic number, it is having atomic number 10. So 1s2, 2s2, 2p6. All the energy levels are complete. Okay, so right here atomic orbitals of neon, atomic orbitals of neon, and molecular orbitals of Ne2 molecule. So atomic orbitals of neon here. Okay, atomic orbitals, molecular orbitals of neon molecule Ne2, and atomic orbitals of neon here. Okay, so as like of fluorine molecule, we are going to draw the diagram. Now in neon molecule, total number of the electrons are equal to 20. 10 plus 10, 20 electrons. So this is the up to 18 electrons. Okay, now 2 electrons are additional there, so we put here 2 electrons now. So this is the MO diagram of the neon molecule. As like of oxygen and fluorine, we are drawing, we have draw here the MO diagram of the neon molecule. So what is the bond order? Number of bonding electrons minus number of antibonding electrons divided by 2. So now you can see here number of antibonding electrons, count. Number of antibonding electrons, this one, antibonding 2, this 4, 6, and this 8. So 8 minus 8, 0. So bond order it is 0. It means that there is a no bond between the two neon atoms. So the neon atom does not exist. The neon atom, neon molecule does not exist, as there is a no bond order, no bond is there. It means that neon molecule does not exist, so not necessary to write here the electronic configuration and magnetic behavior. So on the basis of the MO diagram, we can explain the three important things. First one, it is bond order. Second one, it is electronic configuration. And third one, it is magnetic behavior. As the atom is having the electronic configuration, molecule is also having the electronic configuration. So this is the way to write the electronic configuration of the molecule. Okay. So now let us differentiate between these three molecules. Differentiate between these three molecules. Okay. Let us going to differentiate between these three molecules here. 1 minute. Okay. See now here. First of all, first molecule we have taken, that is hydrogen molecule. So hydrogen molecule, it is having bond order, it is equal to 1, and magnetic behavior, it is diamagnetic. All the electrons are paired there. Second, you can write the electronic configuration also. Okay. After hydrogen, helium molecule, bond order 0. Then this molecule does not exist. Lithium molecule, bond order 1. This is also diamagnetic. Magnetic behavior. Fourth, beryllium molecule, 0. Bond order is 0. Molecule does not exist. Fifth now, oxygen molecule, bond order is 2. That is double bond between the two oxygen atoms. It is paramagnetic. On the basis of the valence bond theory, oxygen molecule, it is diamagnetic. And that is the drawback of the valence bond theory. That is the drawback of the valence bond theory. Valence bond theory could not explain the paramagnetism of the oxygen molecule. But molecular orbital theory explains very well the paramagnetism of the oxygen molecule. Then fluorine molecule, bond order it is 1. There is a single covalent bond between the two fluorine atoms. So it is diamagnetic. As we know, all the electrons are paired in the bonding as well as antibonding molecular orbitals. So it is diamagnetic. And seventh molecule that is known to us, neon molecule. Actually, it is not a molecule because bond order is 0 here. So no question to explain the bond order in the neon molecule. So in this way, we explain the molecular orbital energy level diagrams for these molecules. So how the molecular orbitals are formed? Molecular orbitals are formed by the overlapping of atomic orbitals between the atoms. When the atoms are approaches close to each other for the formation of the molecule, the atomic orbitals of the atom get combined, get overlap, and new orbitals are formed. That orbitals are called as molecular orbitals. If two atomic orbitals get overlap, two molecular orbitals can be formed. One is bonding molecular orbital and other is antibonding molecular orbital. Then there is formation of sigma molecular orbital and pi molecular orbital. So the atomic orbitals like 2s, 2pz are involved in the formation of the sigma molecular orbital, while the atomic orbitals 2px and 2py are involved in the formation of the pi molecular orbitals. So thus, in this lecture, we explain the formation, the molecular orbital energy level diagrams of oxygen molecule, fluorine molecule, and neon molecule.